Hello and welcome to this video on enthalpy and calorimetry. We've been using calorimeters in class already actually to do some lab work, and today we're going to discuss how we can actually use those and do a couple calculations based on that and some other things. So grab your Cornell notes and let's get started. You see right here, this is actually a diagram of what we call a bomb calorimeter. And so we call that, there's a bomb cell here. And basically, this is a pretty advanced piece of equipment. This is just a diagram of it. But all calorimeters kind of have the same general thing. We have some sort of a way that we're going to have a process or a reaction taking place. And then we're going to have something that stirs the water, and it'll sit in some sort of a water bath or be suspended as a solution in water. And then we have to have some sort of a temperature probe or a thermometer in order for us to be able to tell the difference in temperature. And then the sample either can be outside of the water bath, or it can be something maybe possibly suspended in there, or for our purposes we'll actually do something underneath. And so this is a pretty interesting way for us to be able to tell how much energy is involved in both chemical and physical processes. So the first question that we have is just in general, what is enthalpy? And enthalpy that we're going to represent with the symbol H is the heat flow of a system at a constant pressure. And really for us, we're going to call it heat or enthalpy. Either way, we can kind of use those together. And so delta H is the change in enthalpy, and that's what we're really interested in. We can add all sorts of little subscripts and superscript things to it, but it's still the change in enthalpy or the flow of heat from a before and after type of a situation. And it's equivalent to Q in the specific heat equation that we've been working with. So both Q and H are going to represent heat. And so we know, and we've looked at this a couple times already, but the change in enthalpy of a system is equal to the final enthalpy minus the initial enthalpy, or the final heat minus the initial heat of that system. Remember, heat is the flow of energy from warmer to cooler object, and temperature is the measure of average kinetic energy of particles in an object. And they're different things, and people oftentimes get those confused. So just make sure you're very mindful of that. So how does a calorimeter work? Well, we've been using them a little bit, and I think they're kind of interesting in how they actually work. And so we've been using a pretty simple one. You just saw the picture diagram of the more advanced type of calorimeter, but we've been using just the styrofoam cup version of this. And so we have a styrofoam cup, and that styrofoam cup has some sort of a lid on it that's hopefully going to insulate a little bit. So we're going to put a lid on the top of this. And suspended down in that lid, we're going to have some sort of a stir apparatus. So we're going to stir with one of them. And then we're also going to have some sort of a thermometer or temperature probe. And so this would be our temperature, okay, that we're going to take. And then in here, we either have some sort of a chamber or we have some sort of a process that's going on inside of here. So we have some sort of a process or a reaction that's going on inside of there. And really, in order to do this, there's kind of some general steps. So these are our general steps. The first one that we need to know is we need to know the mass of our water. Now, since water has a density of 1 gram per milliliter, we know that if we know the volume in milliliters, it should be equivalent to our mass. So we can easily use that. We need to know the initial temperature, T initial, of our water, okay, and we might also need to know that of whatever process might be taking place, depending upon what's going on with this. We need to also know the reaction or the process, so the reaction and or the process that we are interested in. We need to know T final, which is the final temperature. And we also need to know or be able to analyze using the specific heat equation that we were using. So heat is equal to the specific heat times the mass times the change in temperature. And so this actually helps us to know that. And what we really do know is actually that the heat, so the Q of the water that we are working with, is equal to the negative Q of whatever the process is, or the reaction. And so knowing that, we can actually determine many things, and we're going to take a look at a couple of those. So let me grab my other cursor here. So here's that first one. This is a pretty simple one, and this is asking us how to calculate enthalpy using just a calorimeter. And so it says, what is the enthalpy when reactants mix, resulting in 100 milliliters of water in a calorimeter going to and from, I guess here, going from 25 degrees Celsius to 78 degrees Celsius. So what we know is we just said that the Q of our water is equal to the negative Q of our reaction. And so we have to evaluate both of these. So the first thing that we're going to do is evaluate our water. And so we know that the heat of the water that we're looking at is going to be the specific heat of water. Now the specific heat, the C for water, is always going to be 4.184 joules per gram degree Celsius. That's a constant that we're going to continue to use quite a bit, so make sure you have that written down somewhere. So for all of our stuff, Q is equal to Cm delta T. So we're going to have the 4.184 joules per gram degree Celsius for the water. We're going to multiply that times the mass of water. Now we see this is in milliliters, but remember, since we have 1 gram per milliliter as the density of water, that means for every 1 gram it would be equal to 1 milliliter. So if we have 100 milliliters, it's going to be 100 grams. So something to keep in mind, we'll put a decimal there so we have 3 sig figs. And then the change in temperature. And so this is our final, this was our initial because we went from this to that, so 78 minus 25 degrees Celsius. So when I calculate all of this out, I end up getting a value of 22,175 joules. Okay. Now that is for the water itself. That's how much energy the water was absorbing. And so we know that this is okay, so this is an endothermic process. And the water was absorbing that heat that was given off by the reaction. So in order to find the reaction, we know that it has to be the negative value from the water. So the Q of the reaction then has to be negative, and since we started with 2 sig figs here, it'll be 22,000 joules. Okay. And so this reaction itself is going to be an exothermic reaction. So for every endothermic process, there will be an equivalent exothermic process, and so the endo was for the water and the exo was for the reaction itself. So that's a pretty simple one, just using the information that we know from water. We've also in lab been able to do specific heat, and so I want to talk a little bit through that process with specific heat and these types of reactions. So this is a little more complex, but it's based on the same principle that whatever your heat of your water is has to be equal to the negative heat of the process that's taking place. In this case, we're going to look for specific heat of our unknown metal. So what is the specific heat? Okay, this is what we want to know. For an unknown metal, if 35 grams of the metal was heated to 140 degrees Celsius, this is our initial temperature of our metal. Okay, so the initial of our metal. And placed in a calorimeter with 150 grams of water, so I just gave this to us in mass already, that changed from 25 degrees Celsius, okay, this is T initial of the water, to 43 degrees Celsius. This is the T final for both of them. Okay? So in order to solve this, what I need to do is solve first for how much heat the water was able to absorb, because it's actually an endothermic process for the water. So for the water, we're again going to have our specific heat of water, 4.184 joules per gram degree Celsius. We're going to multiply that times the mass of water. Okay, so there's the mass of water, 150 grams, and the change in temperature of water, which was 43 minus 25 degrees Celsius. And when we put that all together, we end up getting a value of negative 296.8 joules. Oops, not negative, positive. There we go. There's no negative there. Okay, so, but the negative value, since Q of water is the positive and Q of the process, or heat of the process, or enthalpy of the process is negative, that means that the process that we have has to be negative 1,000 or 11,296.8 joules. And what we can do is we can use this value and plug it in to solve for that C value. So if we're using Q equals C, which C is the specific heat, M delta T, we want to solve for C of our unknown. So this is for our process, or for our unknown. Okay, so I can actually put unknown there as well. So what I'm going to do is I'm going to solve for that. So negative 1,000 or 11,296.8 joules is equal to C times the mass of our metal. Okay, so the mass of the metal has to go down here. And the change in temperature. So our final temperature was 43 minus the 140 degrees Celsius. That was our initial temperature of the metal. And I know I've had a couple questions from the lab on the value of C being negative, which it won't be. So now I just algebraically solve for this. Negative 11,296 joules divided by 35 grams. And when I did that calculation already for the change in temperature, I got negative 97 degrees Celsius. Okay. When I calculate that all out, I end up getting a value of 3.3 joules per gram degree Celsius. So there's a lot going on in this problem. You really have to keep straight what things actually relate to. So you might want to watch this section of the video maybe another time or two just to kind of get that down and ask questions when you get to class. All right, let's move on a little bit. So we have these things called heats of reaction. And what are they, or enthalpies of reaction? So we start off with these thermochemical equations. So here's an example of one. And what we're doing is we're showing this value for the energy. So on this side, we put two things together, and on the other side, we produce a product and we produce some energy, which means since energy is part of the products, this has to be an exothermic reaction. And so we know that exothermic reactions have a negative delta H, so this is exothermic. And so we can actually write this a little bit differently, and we usually write these as a heat of reaction, or a way that we would see this. So the enthalpy value of a thermochemical equation under standard conditions, which are 1 atmosphere and 25 degrees Celsius. So a lot of times, instead of showing that plus in the amount of energy, we write delta H, and then we represent this with either a positive or a negative value. Remember, if it's a negative value, then it means that your final had to be less than your initial, and so we would have given off some energy, and that makes that exothermic. We also see these for heats of combustion, and so there's a table in your book that has the enthalpy value to combust 1 mole of a substance, and we can use that. We have these known values from people doing many experiments on them over the years. So let's actually do one of those calculations. And again, we always like to measure things in grams. So how do we calculate enthalpy using heats of combustion? So it says how much heat is produced from combusting 5 grams of sucrose if the heat of combustion for the sucrose is negative 5,645 kilojoules per mole. So there's kind of a two-step process to this. The first one is we have to go from grams to moles of sucrose, and then we're going to go from moles to kilojoules to find out the amount of energy. So I take my 5 grams of sucrose, and for every 1 mole of sucrose, I add up the molar mass. And I already did this, and you get 342 grams. So that is the molar mass. So the molar mass, from adding up all of those masses in that formula for sucrose, is going to be 342 grams. So make sure you kind of look back and check those to make sure you're getting the same amount. Now, when I do this, I'm going to cancel my grams, and I end up dividing 5 by 342, and we get a very small number, 0.0146 moles. Now, I can do this into a two-step conversion if I want to, but I'm going to separate them out. So now I'm going to take that value, and I have this conversion factor. So it says for every 1 mole, there are negative 5,645 kilojoules. I made my pen a little bit thicker there, but it'll work okay. So if I take, my moles are going to cancel here. If I take the 0.04146 and I multiply it times my kilojoules, I end up finding out that this ends up producing 83 kilojoules of energy. And we could actually relate that to calories as well if we wanted to do an additional conversion to go from kilojoules to joules and then from joules into calories. Or we could just go from kilojoules to kilocalories as well. So I hope that was helpful. We'll take a look at some practice when we get to class, and please let me know if you have questions.